Thank you so much again for joining us today in our bi-weekly CDM lecture series. We have a great speaker today, whom I was talking to earlier on, Professor Webb, and he said something great to me. I always ensure that I take my mathematics, I mark the complexity, and I present in layman terms. So today, Professor Webb from Emory University, who is a full professor there in mathematics, from Vanderbilt University in Tennessee. He's a full professor in mathematics, who has co-authored over 190 papers, written one research monograph, and co-edited 6 volumes. He has delivered plenary lectures, colloquia, and seminars worldwide, as well as being a member of 11 archival journals editorial boards. Since 2012, he has been a fellow of the American Mathematical Society. His research interests are in nonlinear semigroups, functional differential equations, infinite dimensional dynamical systems, mathematical population dynamics, mathematical biology, and biomedical mathematics. He employs elementary methods whenever possible, but for more complex problems, he shows a great ability to employ power abstract methods. Again, Elena, please stop sharing. Thank you so much for coming to share your work with us, Glenn. We are looking forward to it, and I read the abstract and such a great talk. Elena, Professor Glenn, please share your screen.
Thank you.
So, share again. Okay, can you see
okay,
me?
it's working.
Beamer? Well, thank you so much for that very kind introduction. And I'm very happy to be here to talk to everyone. I thank you very much for showing up to hear this talk. And I hope I can provide some information that will be helpful to everyone. If you looked at my biography a moment ago, you saw that I started out as a very abstract guy when I did my PhD in my early years. And I gradually became more and more applied. And now I'm quite applied, but I still have a very strong interest and strong devotion to theoretical mathematics, because without it, we will not be able to do anything. And there's a famous saying about mathematical models. I think it's due to George Smart. He said that all models are wrong. Some are useful. And we who do models, we know that. And we hope that our models can be useful. So I hope I can give you some useful information today. You can see my screen okay. Is that, everyone see it okay? There's no problem? Say yes, somebody, or nod your head.
Yes.
Yes.
Okay, good. Okay, here are the goals. Well, as I said, to develop mathematical models to predict the future of COVID-19 epidemics. Well, more than predict, but also to understand the past. But there's a great hope that we can somehow predict what will happen in the future. And this is an extreme challenge, an extremely difficult problem, because there's so much uncertainty in our models, our predictions, the future, because I compared a little bit to the weather. Will it rain in Toronto on November 26th? Well, the Weather Bureau can't really tell us, right? They can't predict the weather that far ahead. They can predict in some ways, but the difficulty is that the information is so sensitive, so difficult to understand at present. To use it to predict the future is extremely difficult. And that's very, very much true for COVID-19 epidemics. But the models, as I said, they'll be differential equations models. And a key feature will be to incorporate asymptomatic infectiousness as well as symptomatic infectiousness, because we know asymptomatic infectiousness or transmission is very important in COVID-19. 100 years ago, there was another terrible world pandemic. And in 1919, 1920, 1918, and it was truly a disaster for the world, a tragedy for the world. 500,000 people in the US died, and our population was half of what it is now. And worldwide, the estimates are vague, but they go to 50 million and so on. So that was a terrible pandemic. and it had asymptomatic infectiousness. And the period of asymptomatic infectiousness was like 1 day, 1 or 2 days, supposedly. It's hypothetical. But anyway, this is an extremely important feature of COVID-19 because the asymptomatic infectiousness period can be quite long, it turns out. Well, then we, of course, number 3, we want to use reported case data to parameterize and initialize our models. And this, again, is a tremendous challenge. As I said, the data is crazy. We'll see that in some examples. And then we want to go forward with our models to try to understand various measures that may reduce the impact of the infectious transmission of the epidemic. And so that's a goal. This is a project underway for all of us. There's so much to do. And I'll just mention one thing to do is to incorporate vaccination into our models, because that's a big challenge. Okay, so I have some collaborators here, and these 3 are involved in this particular project. Xue Liu from Beijing Normal University, and Pierre Magal from University of Bordeaux in France, and Ousmane Sede in Senegal. So we have been working for some months now on these models. And so this is the team, and I work with other people. I'll mention other people, but this is certainly a collaborative effort for the people working in the subject, because we've kind of changed the way we do mathematics and we present mathematics. We want to be fast, we want to be general, and we want to reach lots of people. So there's changes going on in the world of mathematics just because of this epidemic. So we will have compartments, and you mentioned that it's a challenge to try to communicate to non-mathematicians, medical researchers and physicians and epidemiologists sometimes who are not advanced in mathematics. And so I'll show you in the next few Beamer files, one way I try to do this. First, you identify the compartments in your model, and we have the susceptible population. So this will be specified to a location. And later, I'll use the example of Spain. So it could be a country, it could be a part of a country, it can be a state, a city, a continent, a group of countries. You decide what your location is, and you take the whole population of that location at time 0 at least to be the susceptible population. You have the asymptomatic infectious population, that's I of T. They're infected and they're infectious. They can transmit the infection to others, but they're asymptomatic. We'll call that I of T. Then those individuals get reported at some time T. They leave that class I of T and they become symptomatic, and they're either reported in this class 3 R of T, or they're unreported in class 4 U of T. So we have 4 compartments, 4 different populations in our model. And this is, whoa, jumped over something. Oh, I have to, here we go. I wanted to show this one next. This is, somehow I got those out of order. This is what I show the medical people, the people I work with who are not mathematicians. First, I show them those compartments. Then I show them the equations, which don't mean much, but then I show this flow diagram. So we start here with, that's a, if you can see it, there's a S there. That's the susceptible population. And it's the individuals in this population are becoming infected at a certain rate that depends on their numbers and the number of asymptomatic infectious people and the number of unreported symptomatic infectious people. We assume that the reported symptomatic infected people don't create any more infections. That's a strong assumption, controversial, because maybe they do. But if you're reported, then you're typically isolated and you don't then contribute significantly to more transmissions. And if you did cause transmissions to relatives and close associates, that was probably before you got reported. So we don't have R class in here. We just have the I plus U mass action term times the S population. And there's more general ways, as we know, to develop this transmission term. We can have general incidents. We can have many different ways to do it, but this is a simple way. So many features of this model involve simplifications to make it more reasonable to work with and to parameterize. So people become infected asymptomatically in this class, in class I, and they stay in this class I a certain length of time. And I'll come back and talk about that more, but it'll be, well, you can see it in this equation. They stay in this class, they go from S to I. So this minus sign becomes a plus sign. Then they leave the I class and go to here and here, but they leave at a rate nu times I of t. This is a first order loss term in the I class. And the way to understand this is the reciprocal of nu, this Greek symbol nu parameter. 1 over nu is the number of days that they will be in this I class. And our time units here will be days. And we'll take nu to be 1 over 7. So they'll stay 1 week in this class. And that's, again, hypothetical, challenged in many cases, but it's not a bad assumption. And in fact, it varies from location to location. But we'll assume people are asymptomatic infectious for 1 week. Then they go to, and a fraction go here and a fraction go here. And the fraction nu1 goes here to the R class. And the fraction nu2 go to the U class. And they stay in that. They stay there for a period of 1 over eta days. And I, again, will, in my application, I'll take eta to be 1 week. So there's not a clear distinction between symptomatic and asymptomatic symptoms. But we'll understand there's some kind of breakdown between the two. In some way, we can separate the two. Someone might be very slightly symptomatic, but we still call them asymptomatic. But if someone's significantly symptomatic, we put them in one of these two classes. Okay, then they stay in there for 1 over eta days, and they exit to the removed class. Okay, so then we have some initial conditions. Then let's see. Let's go back here to stages of the model. So this is important because in very nice epidemic models, we just have one set of parameters. That's it. They're true throughout the course of the epidemic. They don't change with time. But in this COVID-19 epidemic, it's very clear that the parameters for transmission certainly are changing in time because there's changes in the culture. There's changes in the government response. There's changes going on all the time that lead to a new transmission value, a new transmission rate. So we incorporate those changes in 3 stages of the model. Stage 1 is an exponential growth stage. So there's an index case that enters some location, but maybe that index case doesn't really get things going. It just generates a handful of cases for a time. There's no real increase in the number of cases, or maybe a very slow linear increase. But then at some point, there's a big exponential stage that we can recognize, that we can identify in the very earliest days of the epidemic. We'll call that stage 1. And that's before there's any government response or social measures or any awareness of the seriousness of the epidemic. That was back in, for the most part, in March, maybe April. Stage 2, the government, the society, they recognize the seriousness of this terrible pandemic, and social measures are implemented. And they cause an end to this stage 1 exponential growth. And so the epidemic diminishes significantly. It goes down due to these various measures. And we call that stage 2. And then there's a third stage, which we call stage 3. And these social measures implemented in stage 2 are relaxed, perhaps several months later. And the number of transmission begins to increase again. And we'll assume that these transmissions in stage 3 are due to asymptomatic infectiousness, which again is a simplifying assumption and controversial. But This will be the 3 stages of our model, and they will each have different transmission rates. Okay, so some parameters. We saw this in the equations. The susceptibles become infected at this rate tau, which depends on time, on the S population, the susceptibles, the asymptomatic infected, and the symptomatic unreported individuals. Doesn't depend on R of T. Okay, that's our tau, our transmission rate throughout. And it's very important to observe that it does depend on time. We're going to change it with time. And as I said, asymptomatic individuals are infectious for 1 over new days. We'll take new to be 7. Same for reported and unreported infected individuals will be in their class R or U for 1 over eta days. And again, we'll take eta to be 7. And this fraction F of I class go to the R class, and the 1 minus F fraction go to the U class. So these are basic parameters that we assume. We just assume these. Okay, there's our flow chart again. So let's go to the stage 1, this exponential growth stage. So this is a time interval during which the cumulative reported cases appear to be growing exponentially. And it's very early in the outbreak of the epidemic, and it has an exponential growth. So we'll call this class CR of T. That's cumulative reported cases at time T. And it's growing exponentially. And there's 3 constant here. There's this A value and this B exponential growth constant. And then there's this other term C. Okay, so typically we'll take C to be 1. And then we'll have to identify A and B. So this is a challenge, but we'll take some data and we'll try to fit the stage of that cumulative reported cases data to this formula. And when we do that, it turns out, and we have developed a way to develop parameters and initial conditions from this formula, the ABC formula. And it turns out that our starting time for the epidemic will be the log of C minus log of A over B. So this is justified in the paper associated with this talk. And so this is, it's difficult to say when the epidemic starts. What's time 0 for France or US or Canada? We have to identify it in the model. This is an ODE model. We have a start time, we have initial values and initial time, and this will be our start time, T0 we'll call it, for the epidemic growth stage. Okay, so, and let's see what's going on here. The transmission rate during stage 1 is given by this formula. Remember, this is the general formula for all the stages, but for stage 1, it's this value where tau 0 is obtained from this B value that I got in the earlier story. I obtained a B value here with a fit to data, and I place that B value here, and I have my initial population. I know that, of course, at time 0. And I have the eta and the new values, and this is the F time, this is 1 minus F times new, that's new 2. And the initial time, as I mentioned, is this value here. And then the initial, the value of I at T0 is this fraction here involving B and C and F and new. U of T0 is this value. We'll take R of T0 to be 1. At time 0, there's 1 reported case. And then from all this, and this has to be justified in a certain way in terms of our assumptions in the model and this fit to the data. And we've done this. And in that situation, we can come up with a basic reproductive number during stage 1, which is given by this formula here. It's R0. And involves these various values that we've identified and that we have formulated. And here's the formula for it in the end. So this R0 is good at times T0, the real beginning of the epidemic when it breaks out exponentially. It's no longer good after that. It's changing with time after that. But initially, it has a value which we can determine, and we use the next generation idea to determine this value from the information that we have. Let's see where we are. Okay, so during stage 2, remember this is the government measures are implemented and there's a significant decrease from this exponential first stage growth, and the population goes down, and there's a transmission rate. Again, it has the general formula which takes this shape in stage 2. So there's the value tau 0, which we keep from stage, remember tau 0 is something, here it is, from stage 1, depending on the B and so on. And we take that value, we keep it, and we multiply it into the susceptible population, which is decreasing over time because as people become infected, they're removed. And it's times I of t plus u of t. And again, we assume the reported cases don't contribute significantly to new infections. But then we multiply that by an exponential factor because we assume that there's an exponential decrease in the transmission during this stage 2. And stage 1 goes from time t0 to time t1. Stage 2 goes from time t1 to time t2. So there's a change in this, this is a time-dependent change in the transmission during this stage 2. Okay, that's stage 2. Then stage 3 is really complicated. This is what, after stage 2, there's a period when the epidemic decreases exponentially in cumulative reported cases. But then there's a relaxation typically of measures, perhaps through government control or through cultural or social context, and we call that stage 3. And the epidemic can then change transmission. And so after time T2, remember stage 2 went from time T1 to time T2. Stage 3 begins at time T2, and we have intervals. It goes from T2 to T3, then T3 to T4, and T4 to T5 out to some last interval. And on each of these intervals, there's a transmission going on, and we take the form of the transmission to be alpha n, which is a value between 0 and 1, times the T0 that we've been working with from the 2 earlier stages, times this product. We assume that, as I mentioned earlier, all the transmissions during the stage 3 are due to asymptomatic infectiousness. Reported don't contribute. Unreported, perhaps they do, but if they're symptomatic and significantly symptomatic in stage 3 and they're unreported, usually they quarantine themselves or isolate themselves, their relatives and contacts quarantine and so on. So we make an assumption that this transmission doesn't depend on you, but it depends on each of these intervals that has a value alpha n. And this alpha n has to be chosen so that it fits data. And remember, the transmission is changing in stage 3 over intervals of days. And we have to identify the alpha n, which goes with each interval. It's a value between 0 and 1. Okay, so can you hear me? Hello?
Yes.
Yes.
Yeah,
yes.
we can hear you.
Yes.
Okay, I got this message that I was muted. Okay, you can hear me, good. If you, by the way, if you have questions, please interrupt and ask your questions.
Basically, if you can use full screen, Control L.
Can I do what?
Full screen, Control L.
Okay. Control
L.
R.
L, large L.
Full screen. Maybe I have it here.
Or go to view. Instead of go to view. Yes, and then take full screen. Full screen, come down, full screen mode. Yeah, exactly.
Screen. Sorry, okay.
Yeah, awesome.
Okay, that's bigger, isn't it? Okay, good. Well, we have another class we want to keep up with. And it corresponds to the data, by the way. It's the daily reported cases. And that's our data. That's the data we get. And we have to live with it because that's the data. And we want to connect the model to the daily reported cases. Our model had its 4 compartments, S, I, RU. But we want to connect the daily reported cases to our model. And we do that by introducing a new function, which we call DR, daily reported cases at time t. And it satisfies this differential equation. dr prime of t equals new 1i of t. That's the fraction of asymptomatic infected individuals that go to the reported class. It's new 1 times this value I of t. So this is a rate. Whoa, what happened there? This is the problem. I don't know how to go back. How do I go back here?
Just leave the back button on your screen, the arrow pointing backwards, it will take you back.
Where?
On the keyboard.
Whereabouts? Down here?
On your keyboard, you see an arrow that points, yeah. If you click on that arrow, it will take you backward to the previous.
Oh, okay. So I want to go here. Okay, thank you. Sorry. Okay. I know these things. I just get a little confused sometimes in the middle of a presentation. Okay, so this dr prime of t, this is the input of daily reported cases for the model. It's the daily reported cases. They last 1 day. So this first order loss term is just a 1 times this function because they're in there 1 day, then they're gone. And they have an initial value, which we set. And then from this value, we can get the cumulative reported cases by integrating this term. That's the cumulative reported cases. Integrate that term from time t0 to t, and that will give you the number of cumulative reported cases in the model for time t, and the cumulative number of unreported cases similarly given by this expression. Okay, so we'll use these values. Where are we? Here we go. Okay, so we want to apply this. Let's see that I didn't skip anything. We want to apply this to Spain. I chose Spain. We're working on lots of countries, many countries. It takes some time and to present what's going on in different countries. But we can see that in Spain, we have a typical example that we can try to understand. Okay, so let's look at the background of what's going on in Spain. The first case was reported on January 31st. March 13th, cases had been reported in all 50 provinces of Spain, and a state of alarm was declared by the government and social restrictions imposed. May 2nd, several months later, they eased these government restrictions. So these will allow us to identify our phases. We'll get our phase 1, 2, and 3 from the data and from this understanding of the background in Spain. Now, June 21st, the state of alarm was ended that had been imposed on March 13th. July 6th, seropositive studies showed that approximately 2 million people had been infected. So we have an idea about the total number of people infected. That included those, since it was sero study, it included asymptomatic and symptomatic infectious people. July 17th, there was a resurgence of daily cases. It started to grow, reported daily cases. August 17th, new government social restrictions imposed. September 4th, a new record of daily reported cases, approximately 10,000. October 1st, about 6 weeks ago, a state of emergency in Madrid and a partial lockdown. And October 25th, a couple of weeks ago, a national state of emergency and a national curfew imposed. So that's the background we want to try to capture. Okay, so here's some data. Someone have a question? Okay.
No, there's no question for now.
Okay, so here's data for Spain. And so this is quite interesting. I can't quite get rid of everybody, so I don't know why. Maybe if I try to make it smaller. But you can see the data. This is daily reported cases data for Spain. And it reflects this information I just gave you about the background in Spain. This, by the way, is from Worldometer. There's the website. they have data for many, many countries. And this is current data for Spain through November 1st, I think it is. November 1st. Whoa, this is, I can't keep up with this very well. Okay, I think you can see everything. And what we see about this data is that it's a mess. It's just a crazy zigzag going on here. We see some trends for sure, but day by day it's jumping like crazy. And so this data is difficult to manage. And by the way, I will mention that Worldometer, the data, I didn't take this beyond November 1st because they change it. The data they have today for December, or rather November 12th, they'll change it 2 weeks from now. So they go back and they change it for various reasons. So I'm going to, and quite significantly sometimes. So I'm going to stop it at November 1st, but we do have data beyond. And what we see, of course, is a scatter, zigzag going on. A single day can jump tremendously from that high value there. The next day, I guess, was maybe that one. So that's, or maybe even that one, in fact. So it's jumping around like crazy. And we have to live with that. That's our data. We must live with it. Okay, so we take that data and we convert it to our cumulative reported cases. These are the daily reported cases. We add it up day by day by day. And when we do, we get a nice smooth increasing curve because we're adding, and that's somehow adding day by day by day takes a lot of the zigzagging out of it. And we see, again, we see some trends. We see the initial exponential outbreak here, which we'll have to identify. We see the exponential decrease in that exponential growth, and it calms down and it stabilizes for quite a time. But then there was this second wave that began. And in fact, there's even a third wave going on here as well. So this is the cumulative reported cases. And that's data. And that's data we will work with. Okay, so one way to handle, and it's done routinely now, you take your daily reported cases and you take a rolling average. And you can take an average over a week or 4 days or 10 days. Here we have a rolling average over a week. So we took the data back here, and at day 7 here, March, whatever, 7th, I guess it was, we averaged the first 7 values here, added them, divided by 7. Then we went to the next and took 7 days back from that value and divided by 7. We got the rolling weekly average in this way, and it looks like this. So now this gives a lot more information than the cumulative cases, because we see some clear trends here. I can't get rid of you, sorry. Can you see that? Okay, there we go. So this is the rolling, we call it the rolling weekly reported cases. And we see a first initial wave, and a second, and perhaps a third wave here. So this is very important data, and we need to smooth that data in some way to understand what's really going on. Okay, so going back to our stage 1, we want to identify in the cumulative reported cases back here, in this early stage of the epidemic when it's clearly growing exponentially, but it's different. It looks, you might claim that's exponential there, but it's really pretty much a straight line or varying, not exponentially. But anyway, we have an exponential phase back here that we must identify for our stage 1. So we have to take an interval. This jumps around like crazy for some reason. We take an interval from March 4th to March 11th. So here's the data. This is the cumulative reported cases from March 1st to March 15th, very early stage of the epidemic when it was exploding. And we identify an exponential phase beginning March 4th and going to March 11th. Before March 4th, we say, well, that was pretty much linear. After March 11th, again, linear. But right in here, it's exponential. So that's a choice, and we could argue for or against it. But when we choose that interval of time from March 4th to March 11th, and those whatever 8 days, I guess, or 9, we try to fit that with an exponential formula, a e to the bt minus 1. And we can do that with a program. And we identify a value a, which is this here, 2000 something, b 0.23, and we, as I said, we took c to be 1. And so we have a formula to fit this data, and the red graph is based on that formula. And from that, from the AB, we get the T0, the tau 0, and the initial values in the way I mentioned earlier. Now T0 turns out to be minus 33. It's a bit artificial the way this is done, because that would be early February. But remember, our first cases were somehow in early February. So we can take T0, which will take to be this value here, to be minus 33. And so again, as I say, it's a bit artificial, but it works, and that's what counts. And from this, we get the value of tau 0, which has this expression here, and we get the initial conditions. So that's how this works for that first stage. Let's see here. Okay, remember we get the R0 value from these at the first stage during this exponential growth factor stage. And here we've graphed R0 on the vertical axis, and its value, by the way, is 3.4 from this fitting of data. And and so that's the intersection of these two yellow lines. That's 3.4 on this axis, the vertical axis, and the tau 0 was something, that red plane, it was approximately that value right there, and the F was something, well, F will take to be 0.4 in the Spain model. And so we have our R0 of 3.4, that's quite high for our baseline value. But if we varied F, if we increased F, we go this way in F, increase the fraction that are reported, then R0 goes higher over here. If we increase, I think it's hard to see, isn't it? If we increase tau 0, then again, R0 gets worse because we get more infections. So R0 is this plane, this surface here, this orange plane is 1 value. We see R0 above or below the value 1 according to this graph. And the baseline value is 3.4. Okay, so we want to develop the transmission values. I have to keep up with the time here. For stage 2 and stage 3. For stage 2, we choose a mu value. That's how we get this shutdown of the stage 2 from government measures and so on. And we chose mu to be 0.09 to fit the data. In stage 3, we have these intervals, and on each interval from T2 to T3 and T3 to T4 and so on, you have a different alpha n. And we choose the alpha n according to the data, again, of the cumulative reported cases. And the way we do that, we recognize that I prime of t has this expression here, approximately. And so we solve that equation for I of t, and we come up with this expression here for I of t. And we can identify an alpha n value in a particular interval from Tn to Tn plus 1 that matches the data fit there. And so, where are we? So in this way, sorry, I can't keep up with which one I'm going. Okay, so we now have our time-dependent transmission rate in all the stages. In stage 1, it had the certain value, which we identified. In stage 2, that was from before March 8th to March 8th. In stage 2, it goes from March 8th to March 30th and has this expression here. and with the choice of the mu value. And then stage 3, it has all these transmission rates on these successions of intervals. And here are the way we chose the intervals, and here are the way we chose the alpha n's. This value here in this column is an alpha n associated with each interval. And we choose these alpha n's according to whether the I prime of t, the cumulative reported cases, which you get from I of t, is concave up or concave down. So I'll show you how that works. Where is it? Okay, so I'll jump ahead. So the alpha n values are chosen according to this formula, which gives us the C. Here are the form. This gives us the CR double prime, the concavity of CR. This is the concavity. This is the growth rate. It's gaining or losing according to which interval you're on. And here's the cases. Cumulative reported cases are given by this formula right here, I should say. So here's CR prime of t. It's of course an increasing function. CR is cumulative, so it's increasing. Now sometimes you look at data like Wikipedia, and they change it, and CR decreases. That can happen, but for us in the model, CR is increasing, and this is the way it's increasing at different rates of increase, always positive. Now the concavity here is either up or down. And that's the way we choose alpha n. We look at the intervals when it's positive, and we choose alpha n so that it gives us a positive increase here that matches this formula here approximately. If it's negative, it's down here, positive here, negative, and so on. So going back now. So that's the way we chose these alpha values according to those concavity changes. And then we have our graph now for our cumulative reported cases through all 3 stages. And this is the match to the data. Well, I wish I could get rid of us. You see it matches pretty well. The blue graph is the model from March 1st, I think it was, to November 1st. The purple dots are the data, and we get a good fit. And then down here we have the U class up here, this cumulative unreported cases, the green graph, and the R of t and the U of t down here, the whatever that is, purple and red. So we got a good fit to data. We can be happy with that. And now we also, let's see if I got what I want. We've already seen this one. We also want to fit our daily data compared to the model. Remember, this crazy graph here is the daily reported cases, and it has quite a zigzag character through here. But if we compare to the model daily reported cases, remember that was DR of t. That's this blue graph. And here, now we look at the blue graph, we see the trends clearly. We see trends in the blue graph, which is from the model. It's the daily reported cases from the model, which settles quite a lot. Now, if we go back to Worldometer, we have a bunch of graphs here. We have, in fact, it goes out to November, I think goes out to November 11th, yesterday. And this is incorrect. I should say November 11th. And we have three graphs here. Gosh, sorry. We have the 3-day moving average, which is the light blue. You see the wiggles in the light blue. We have the 7-day moving average, which is the dark blue, which looks very much like our model. And then we have the daily cases, which are these vertical gray bars. They're jumping around like cases, crazy. But we get that data through yesterday. But notice in the last 2 weeks here, this is why I ended this at November 1st in my model, because it's so hard to understand what's going on there. And in fact, they'll change this next week. They almost always change it. So it's settled here up to about November 1st. So we'll keep it November 1st. Okay, I have to watch the time. I know I'm almost done, I think. Okay, so here we go. Oh, sorry. What's that? Okay, we want to compare. Did I already talk about this? I don't think I did. This is a comparison of our model simulation to the rolling average daily reported cases data. So those purple dots are the rolling 1 week average data, and the purple graph or the dark blue graph is from the model. It's what we call this the DR of T. It's the daily reported cases from the model compared to the rolling weekly average daily reported cases. And so we see a nice fit there. So this is how you get those alpha values. You look at these intervals, which I haven't identified here, but we take each interval when we see some change going on, like right here at the end, and we develop an alpha n that corresponds to some interval for all these various changes. Okay, I'm almost finished. One thing we try to do with our model is to go forward in time and predict. So this is an example of that. Our model goes out to November 1st compared to the daily reported cases averaged weekly data, and agrees nicely. So we can just extend our model. Let's just take it out to December 1st. We ended it at November 1st before, but let's continue it. Now I don't have the data, but we'll take 3 cases. We just keep the same last alpha n value, whatever it was. So this will just continue this decrease for the next month. That's the dark blue here, no change. If we decrease social measures, that's the red graph, and there'll be a new wave that will take off in the next month. And that goes with this particular value, higher value for this against tau 0. And if we increase social measures, that's the green graph. We'll do even better, and we'll see how we can bring this epidemic even further down in daily reported cases. And so these are 3 extensions of the model to the cases of no change in the tau multiple of tau 0, increase in that multiple, and a decrease. Same, worse, better. And we can use this, and we can take different intervals of time, different values, try to understand how to predict this epidemic 1 month ahead. It's very difficult to go 6 months ahead, impossible. It's very, very difficult to go 2 months ahead, to go January 1st, but we can try to go forward and predict, like the Weather Bureau is predicting the rain next 2 or 3 weeks in Toronto. We can try to predict based on information that we have using this model. Okay, some conclusions. I'll just say this quickly because my time's pretty much gone. Here's the conclusions and just a review of the model itself and the application to Spain. I want to mention some work with our team, and there's some other people involved in this besides the 3 on this particular talk, and some names are given here. And so I have then thus concluded my talk. So if anyone has a question, I'll be very happy to answer. I'll try to answer any questions you have. Maybe I'll keep that one up. So thank you. Thank you all very much. I appreciate it very much. Thank you.
Thank you so much for the great talk. Such a great talk. Like we started on, and you were telling me how you do your best to ensure that you take it to a layman and people understand what you're doing. That's exactly what you did, and I really appreciate it. Thank you. Please, the floor is now open for questions. Feel free to either type your questions or come on air and ask your question. Elena, do we have any question there?
Yeah, so we have one from the chat, and then I think we have Russ Grainer as well asking a question. So I will go over the chat and then I'll ask the questions from, yeah, thank you. So Zisheng is asking, well, thank you very much for the informative talk. Do we know what is the cause of the increase around October 1st?
Well, as I mentioned, there was a relaxation of the measures that were implemented. Whoa. Well, very early in May, in June 21st, they ended the state of alarm. But by the end of July, there was a resurgence of cases. So I would say that we don't really know well why there was such a change in early October. It was going down and then suddenly it starts to go up. But it could be there could be many reasons. This is a mystery in a way. Was it due to social changes? Did people relax their social behavior in Spain? And there were more contacts, less social distancing. Were the government closings relaxed, either officially or perhaps unofficially? So it's possible that that's an explanation, but there's other possibilities. It could be that there was a different strain, a mutation in the strain. It was somewhat different, and it led to a new outbreak. So clearly there was an outbreak here. We understand that because government measures were relaxed throughout here. But there was this third wave here. And so why? It's not clear, but there's different possibilities. Those are some possibilities. Will there be a fourth? It's not clear what will happen here. Will there be another wave going up, or will it continue down or go down even more? So this is difficult to understand.
Thank you.
Thank you, sir.
So you can ask a question now. Thank you.
Thank you. So thank you for a wonderful talk. That was fascinating. We're actually doing something fairly similar to this idea of having asymptomatic and not as well symptomatic, using common filters to model it. My question I want to ask is, the way you described this work, you talked about identifying regions and then fitting parameters by you yourself identifying regions. Can that be automated? If I say, here's a data set, can you find the regions? Or if I give you a data set and also tell you policies that were implemented, there ways to automate the process of finding the parameters and using that to do perhaps better forecasting?
That would be a great accomplishment to do that. I can tell you that it's not easy to set the data for Spain because, well, there's 8 months or whatever, daily data, and it can be done. I did it, but it's kind of just a challenge, a personal challenge. What you suggest is having some automated way to do this. Choose a country, take the data, and set everything up and let it go. Click enter and see if it'll generate something like this that we can alter in this way and that way. And that's our goal. We want to, as I mentioned, we want to do many more countries, and we will try to automate in some way because it's just, but in a certain sense, it's not easy because, as I said, choosing these alpha n values amounts to understanding the concavity changes right here in this CR function. Here's the derivative of cumulative reported cases. It's just increasing, but clearly it's increasing in different ways. The increase rate can go down or go up, and the concavity is also very important because if the concavity is up, it's getting worse. If it's down, it's getting better. So when it's negative, it's getting better. When it's positive, it's getting worse. But we have to take lots of intervals to account for these various changes. This could be improved even in this presentation, but it would be a very useful accomplishment to do this automatically, to take our data for a location and enter it into this model formulation and try to do it automatically. So that's a goal. As I said, we're going to do more countries. France, very.
We should definitely chat later on because we're doing something very similar using machine learning approaches. But thank you again for a wonderful talk. I got a lot of good ideas from it. Thank you very much.
Thank you. Thank you for your question. Of course, machine learning is a very important goal right now to apply to many, many things, certainly to apply to COVID-19 epidemics in locations. Not only locations, by the way, age groups. That's very important. And also vaccination groups, very important. And geographies. By the way, we're trying to do this geographically for some countries, in particular for Spain. We have that project going on, and the epidemic swept around in a certain fashion through Spain, and we're trying to match that. And so that's important. Many aspects of this, and machine learning would be just really so useful, so valuable.
The good news is there's lots of data from many different countries at a daily basis, at a regional basis. So as a machine learning person, I'm very excited to see that. But yeah, thank you very much.
This is a big data problem for sure.
Thank you. So Amelia is asking if you could please show your conclusion slide. Amelia, do you have any question on that? Or was it just to read the conclusions? So I don't see any question from her. I think in the meantime, I can ask another question from Yuming. So thank you for the talk. And then, is it necessary that the asymptomatic and unreported individuals have the same infectivity?
Well, that's an underlying assumption, yeah. But remember, we're changing it on time intervals. But it's a good question. Why would they have the same infectivity, infectiousness? As I said, there's simplifications to cut down the number of parameters we have to worry about. So that's one way to reduce the number of parameters, just assuming that they cause the same number. But I agree that it's a good question, and perhaps the model should be generalized to allow for that variation. But that would introduce a bunch of more parameters that we have to try to understand. And how do we do that? Because the asymptomatic infectious class is in some ways unknown currently, although we have testing. If we had very good testing, we could do this. But I agree that's a strong assumption, a simplifying assumption.
Thank you. And we have another question from Xiao Jiang, sorry. For different time intervals, is it useful to compute the corresponding R0?
Yes, we could do that in the same way, because we take our information from the model, and we can use that information in the next generation method to compute the R0 on every single. That's a good point. I haven't done it, but it clearly illustrates in a very direct and upfront and understandable way to everyone what's going on in the epidemic. R0 on each. Thank you for that suggestion, because that could be done easily, and we could graph the R0, and it would give us an immediate understanding of the stage of the infectiousness in the epidemic on all these different intervals and so on, different stages of the epidemic.
Thank you.
I would say R0 is, we know R0 well, and we use it so effectively, and we understand it so well. But in some cases, R0 is exaggerated a little bit in its value, because it's not a perfect description of what's going on for all time through an epidemic. It's dependent on what's going on in changing aspects of the epidemic. So when we say R0 is 3.4, what does that mean? It applied to a very early and a very limited time for the epidemic. But calculating it as a time-dependent function would be very nice.
Thank you. Elena, we still have room for one question.
So I don't see, oh yeah, actually there is just one by Feng Ying. Does R0 change when you predict the next month?
Yes. Remember, R0 was only for this first stage, which was this limited time when the epidemic was growing exponentially. It was clearly in an exponential growth phase. And we fitted an exponential function to that data. And it involved an A and a B and a C. And once we had the B, I think, then we could plug it into this formula for R naught. We already parameterized a nu to be 1/7 and A to be 1/7. And this is this nu 2 and so on comes from the F value, which we said was 0.4. By the way, that's another issue. Why should we claim that 40% of cases are reported and 60% are unreported when they become symptomatic? That's a strong assumption, and sometimes the value is much higher for unreported, 10 to 1, not just a 3 to 2. And so that's another consideration that has to be evaluated. But here we assume that the majority of cases that were reported that were symptomatic were unreported, but not 10 times, not 5 or 3 times even. But anyway, once we hypothesize an F value, we get an R naught for that first stage, and the formula is here.
Thank you. Let's take the last question, which will come from Pei Yuan. Pei asks, thank you for the talk. I want to ask about how to determine the U of T0 and why it is not an integer.
Well, again, that's, as I said, this fit is in the identification of the parameters that it gives, and the initial conditions are artificial in many ways, because of course that should be a integer, but the model doesn't know that it's dealing with integers. Remember, the model is a continuum construction, so it doesn't mind. We took that to be 1 just because it doesn't make much difference what its value is, but we want it to be some low value. And I forget what U0 turned out to be. What was it? Where was it? I forget, here somewhere. It turned out to be 0.92. Well, as I say, it's artificial, it doesn't matter so much. And this initial time also doesn't matter so much in terms of their actual factual character. What matters is that it gives this graph here. And once we have that, we can take off from that. So it gets things going. And that's a tremendous difficulty using data to fit ODE models for COVID-19. You have to identify your start time and your initial values, your parameters, and it's a big challenge. And there's different ways to do it. There's all kinds of ways to do it. This is the way that we developed that works. And that's, remember, all models are wrong. Some are useful perhaps, but perhaps this is useful. It works. And so we're converting, the differential equation is very much averaging behavior over a continuum, and that behavior is very complicated, daily and zigzaggy and so on. So it's a big challenge to identify these initial values and parameters.
Question from the director of the Canadian Center for Disease Modeling, Wai Ping Zhu. So will you mind coming on live and ask your question, Wai Ping?
Yeah, in fact, like, thanks, Glenn, for this wonderful talk. In fact, I want to add something. Glenn has been a friend of CDM for years, supporters. In fact, he's also a great teacher and friend of many of the CDM members. I want to thank him, especially for, that many of us know that his characters and his mathematics and the way of doing mathematics, in fact, are the real models for many of us. So I want to thank him again. I also want to say, like you see now, it's midnight in China. We have people from States, we have people from Europe, many friends, audience from China. Now it's the midnight over there. So I want to thank all of them. I would hope that, so when this terrible pandemic is gone, you see Glenn, also I see Pauline is online listening to your talk too. You see who invented the R naught formula for all of us. You see, I'm looking forward. You can like visit Toronto after this pandemic is over. Stay well. Thanks, everybody. Back to you.
But thank you very much for your kind remarks, and I appreciate everyone, especially people who are up very, very late at night. Special thanks to Pauline, who's such a good friend for so long and such a important contributor to this subject. And I thank all of you, and I wish you well, and I hope you will stay safe and your families will stay safe and you will be careful. And I hope we get together and meet in person someday, somewhere. And I really believe that will happen. So again, thanks so much. Thank you all.
Thank you for coming, Glenn. Thank you very much for coming, everyone. We have a lecture series like this every bi-weekly. We'll send emails out. We already sent a list. If you are not on our mailing list, please do add your email to our mailing list. We'd like to have you be part of the CDM family. Glenn, we are looking forward to having you in Toronto, to working with you and discussing with you. I love your talk, and I think our audience do. Thank you so much. Please, we're looking forward to having you next time. Let's give the last hand of applause to Glenn, our great speaker, for the great job.
Thank you.
Thank you. Thank you very much.
Yeah, take care. Stay well.
Thank you.
And see you in Toronto soon.
Okay,
Bye.
for sure, for sure.
Yeah.
Thank you. Bye.
Bye-bye.